this arc is being created by two charged bodies. One is a positive charge, the other a negative charge. In this case, the force is great enough to cause electrons to leave the negative charge, travel through air, which is an insulator, to the positive charge. We've also found that a battery has two charged materials. If a connection is made between them, electrons will leave the negative charge and travel to the positive charge. Well, let me make such a connection. And you see the results. Though the pressure is small, it caused enough electrons to flow to burn the wire up. Now, this force is called an electromotive force, or an EMF. It's electromotive because it motivates electrons to move. Now, other terms used to identify the force is electrical pressure, difference of potential, but you'll probably see this one used most often, voltage. Now, regardless of the term used to identify the force, the unit of measure is identified as volts. Now, I'm sure you've heard the expression, a 6-volt battery or 110-volt outlet. Well, in this discussion, we're going to see some of the common ways of producing an EMF, or voltage. Now, keep in mind that the basic requirement is to develop two charges, one positive, the other negative. Now, one method of developing a voltage is by chemical action. I'm going to build a chemical source by using a piece of zinc, carbon, and sal ammoniac powder, a chemical made up of chlorine and ammonia. Now, I'll mix water in the sal ammoniac so that it's in a paste form. Now, by mixing water in, it should activate the chemical, make it more active. Mix it up real good. Now I'll put in the zinc here and the carbon here. Now, here's what will take place. The sal ammoniac will react with the two materials and cause the zinc to gain electrons, the carbon to lose electrons. The zinc then will become negative, the carbon positive. Now, an EMF or voltage will exist between the two. Now, to check the results, I'm going to use this meter. Now, if a voltage or EMF does exist, it'll force electrons through this meter, causing it to deflect. So let's connect the meter to the material. One side here to the zinc, the other side here to the carbon. And of course you can see that the meter does deflect. Well, actually this is a crude form of dry cell battery. The two rods are called electrodes or terminals. The chemical is called an electrolyte. Well, a flashlight battery is an example of producing a voltage by chemical means. Now, by taking a look at a cutaway view, we can see essentially the same elements as the battery I just built. Now, the center post is a carbon rod. It develops the positive charge. The battery case is zinc. It develops the negative charge. The electrolyte is basically sal ammoniac powder, and it's packed between the carbon and the zinc. Now, this type battery develops an EMF or a voltage of about 1.6 volts. Here's another example of developing a voltage by chemical means. Its makeup is about the same as the flashlight battery. Taking a look at it, we see a carbon rod in the center, a zinc case, and a sal ammoniac electrolyte. Now, this battery also supplies 1.6 volts. In other words, the carbon-zinc combination generates 1.6 volts, regardless of the size. The chemical combination determines the amount of voltage. A car battery is another example of developing the voltage by chemical means. In this case, the electrolyte is sulfuric acid diluted with water. The electrodes are sponge lead here and lead dioxide here with a separator in between. Now, basically, this battery develops the voltage in the same manner as the dry cell. The chemical reaction will cause the lead dioxide to become positive and the sponge lead negative, so a voltage will exist between the two. One cell of this battery develops about 2.2 volts, so to furnish the voltage required in most cars, 6 cells are arranged to develop an output of about 13.2 volts. Checking the cell arrangement, we would have about 2, 4, 6, 8, 10, 12, the ordinary 12-volt car battery. Now, as you've probably realized, the chemical method is an effective way of producing an EMF or voltage. Another popular way is by mechanical means, commonly called the induction or generator method. In this method, all that's required is a magnetic field, a conductor, and motion between the two. Now, a magnetic field is similar to the field around a charged body. We can get an idea of how this field exists by using iron filings and a magnet. I'll sprinkle some filings on the glass covering this magnet. Notice how the filings form into lines, indicating the shape of the magnetic field. Well, when a magnetic field is brought near a conductor, it will force the free electrons of the conductor to move toward one end. The end that gains electrons will be negative, the end that loses electrons positive. Since charges are developed in the conductor, a voltage must exist across it. Let's demonstrate this method. Now remember, we need a magnetic field, a conductor, and motion between the two. Well, here's a magnet. It'll give us the magnetic field. This coil of wire, insulated wire, is a conductor. To check for a voltage, I'll connect the conductor across the meter. One side and the other end of the wire. Now, when I start moving the conductor, notice that the meter indicates a voltage. Now, it doesn't make any difference how the motion is attained. The magnetic field or the conductor could be moved. I've elected to move the conductor. The important thing is there must be movement between the two, or relative motion. Now, notice that the meter needle swings back and forth as the conductor is moved. This is because the field will force electrons to one end of the conductor and then to the other end. The result is an alternating or AC voltage. Now, you'll talk about AC in detail later on. For now, you should realize that it is different from that voltage we developed by the chemical method. Now, why do we say voltage is produced by mechanical means? Well, to obtain the motion, I had to mechanically move the conductor. Generators and alternators use this principle to develop a voltage, and the motion is usually developed by rotating the conductor. A voltage can also be produced by applying heat to certain material. For example, if I connect this device to the meter and apply heat, we should get an indication of voltage. Let's try. Applying heat to the device, notice that as it heats up, the meter indicates a voltage. The more I heat it, the more voltage. Now, if I take the heat away and let it cool off, the needle slowly moves back. Now, if I help cool it off so that it's at normal room temperature, no voltage will be produced. Let's try it again. Applying heat, we get an indication of voltage. Now, a device that develops voltage in this manner is called a thermocouple. This illustration shows how the voltage is produced. When two dissimilar metals are brought into physical contact and heat is applied to the junction, free electrons will move from the more dense to the less dense material. The result is a deficiency of electrons in one material and an excess in the other. One material has developed a positive charge, the other a negative charge. Therefore, a voltage exists across the two. Now, of course, the amount of voltage produced by this method is limited, but due to its sensitivity to temperature changes, it's often used for temperature measurement and in temperature control devices. A method similar to the thermocouple utilizes light rather than heat to produce a voltage. Now, devices in this category are made up of metals sensitive to light energy. When light strikes the device, electrons in the sensitive metal will become free and will travel to the film. The film gains electrons, therefore it's a negative charge. The metal lost electrons, so it has a positive charge. Charges have been developed, so voltage exists across the two materials. Well, this method of producing a voltage is the photoelectric effect, and some of the devices that use it are photocells and solar cells. This is an example of a photoelectric device, a small solar cell. Now, by connecting this device to the meter, we should be able to see that the only requirement for developing a voltage is light. Let's try it and see. Connecting it across the meter, I'll use this lamp as the light source. Now watch what happens as soon as I turn the switch on. The meter indicates a voltage. Then this little device produces a voltage simply by using light. Now if I bring the device closer to the light, notice that the amount of voltage increases. More light, more voltage. Quite an amazing little device. Now, some uses of the photoelectric effect are to indicate light intensity, as in this light meter, and the solar batteries used to supply voltage in some space vehicles. Another amazing little device is this one, a crystal. It employs still another principle to develop a voltage, the piezoelectric effect. Now, the piezoelectric effect is this. Some crystalline materials possess the characteristic that if stress is placed on them, they produce a voltage. And the reverse of this principle is also true. That is, if a voltage is applied to the crystal, it will produce stress. This simply means that the crystal will vibrate or oscillate. It's difficult to show this method practically without advanced equipment. To apply enough stress to this to cause it to develop a voltage large enough to measure is impossible without breaking the crystal. However, later in the course, when you come to understand a few more principles, we will apply a voltage and check for an output from the crystal. Now, some microphones and some phonograph needles employ this technique to develop a voltage. Okay, we've developed a voltage by using a chemical with mechanical energy, by applying heat, with light, and we discussed the piezoelectric effect. In each method, voltage is produced by creating a positive and a negative charge. Now remember, these are some of the terms used to describe this force. We said that voltage is the one that we'll see most often, and that we'll be referring to volts. Now, as you progress in your training, you'll see examples of how each method is used in actual circuits. Now, a little bit later on, we'll come back and see the relationship of this voltage to electron flow. I'll see you at that time.